Welcome to the last video in our electricity unit, and you might think that this is different from electricity because it's called magnetism, but it turns out that electricity and magnetism are far more similar than you think, and actually far more similar than most people thought until about 170, 200 years ago. Magnetism, like electricity, happens due to the effects of electric charges. And like I said, people did not realize this until rather recently in terms of just human history, that magnetism and electricity were more or less the same thing, but like two different sides of the same coin. Okay, I believe it was a famous scientist, physicist called John Clerk Maxwell who first discovered that these two effects are related. Specifically, magnetic effects occur when electric charges move. And I do have to give a little note about this video. Magnetism, there are some great, absolutely phenomenal demonstrations that go along with magnetism that you'll really like. However, they are best done in person. It's very hard to film them and show them and narrate them at the same time. So this is going to be basically just a set of facts that you're learning right now. We're going to see the application of those facts when you're in class. We're going to do all of these demonstrations that we would otherwise be doing. So just so you know, this is going to be, we're basically just going to be, kind of giving you some facts about how magnetism works and explaining some things. In class, we're going to see exactly how those facts get applied. So anyways, magnetic effects occur when electric charges move. Here's a stationary charge. Okay, we know let's say it's a positive charge, so it's got a little electric field coming out like this, straight away from it. And I'm saying it's stationary, so a stationary charge creates only an electric field. Okay? If it's not moving, it only creates an electric field. However, if we take that charge and then we move it, and these aren't field lines, these are just my little artistic lines to show that the charge is moving. A moving charge does something different. If a charge is moving, it actually creates both an electric field and a magnetic field. And you might be asking, well, how does that work? How does it create both? The straight answer is it just does. Okay, there's some very complicated math that we can get into dealing with how electric fields change as a particle moves. Basically what happens is the effect ends up appearing as what we would term a magnetic field. Okay, so electric fields and magnetic fields are really basically the same thing. They're both created by electric charges. It just so happens that a magnetic field, the effects of the magnetic field only show up when that charge is moving. So you might be asking, well, what about like a permanent magnet then? Like a bar magnet with like a north pole and a south pole. How do those work? Well, permanent magnets are just pieces of metal, usually, that have all of their atoms aligned in a certain direction. The atoms are like tiny little magnets themselves. When they add together, they create a larger magnet. We've kind of got a picture of this here. You can imagine all of the little atoms as being represented by these arrows. And these arrows, I'm not going to get into exactly what the arrows are, but they have to do with the direction that the electrons in those atoms are orbiting the nucleus. Basically what happens is in an unmagnetized piece of metal, the orbits of those electrons are all completely misaligned. They're all kind of all over the place. If you then magnetize that piece of metal, what it does is it lines up all the orbits together. Okay, it lines them all up so that all the orbits, all the electrons are orbiting in the same direction. A magnet just has all those atoms where they're all orbiting in the same direction. All the electrons are orbiting their nucleus in the same direction. It's like frozen in is the best way to describe it, where those electrons can't get out of alignment anymore. Okay, so something that's non-magnetized, you've got these electrons just all aligned in super weird directions. For something that is magnetized, or a magnet itself, all of the atoms are lined up so that all the electrons are orbiting in the same sort of direction. So again, alignment has to do with the direction that electrons are orbiting inside the atoms. And that's pretty much all you need to know for why something has magnetic effects. It boils down to what direction are the electrons orbiting inside the parent atoms. As you probably learned in elementary or middle school, each magnet has a north and a south pole with the same attraction repulsion properties as electric charges. Namely, like poles repel each other, opposite poles attract. I guess you do lose the neutral and charged attraction, but like poles repel each other, opposite poles attract. We can investigate magnets by using something called a compass. A compass is used to tell the direction of a magnetic field. Typically, a compass has two ends. One is either colored red or white, the other one is colored black. They're not all going to be like that, but a lot of them are like that. The red or white end always points towards Earth's magnetic north pole. So let's think about that for a second. If you have an end of something metallic that is pointing towards Earth's magnetic north pole, wouldn't that mean that the pointing end is actually the south pole of the compass, or of the magnet? Oh, this should say compass. Compasses, the reason they work is they are little magnets. They can be affected by magnetic fields. So if you have a compass that points towards the Earth's magnetic north pole, not the geographical north pole. The magnetic north pole is something different. You might have heard about in the news, like the poles flipping or whatever. You don't really have to worry about that. Earth's magnetic north pole, if you have something that points towards that, then that must be the south pole of that magnet. In other words, the south pole of the compass points towards the north pole of Earth, which is a little confusing for people. So here's a compass. Oh, you know why? Okay. I have my magnets all in here, so that's why they were under this piece of table, or this desk, so that's why I was throwing it off. So I have a compass here. It is not, if you can see it, it's pointing kind of up towards the page. So it doesn't have a red or a black or a white part to it, but it does have a little arrow, and the arrow is pointing in that direction. So it's pointing to the north, and that's pretty accurate. North, I think, is a little bit closer off to that direction, but this is good. This is pretty accurate. So what we have here is if north is this way, if Earth's magnetic north pole is in this direction, and that part of the compass is pointing towards the north magnetic pole, this is actually the south pole of the compass. This is the north pole of the compass. It points towards Earth's magnetic south pole. So that can be a little confusing sometimes. But I'm going to draw compasses like this. I'm just going to draw kind of a diamond shape. I'm going to color in the red end. And I'm going to leave the other end to be white. Usually it would be black, but that's fine. North, west, south, east. Since this end points to the north, this is the south pole of the magnet. You just have to remember that it actually points north. South pole just means that's the end that points towards the north. It's one end of the compass. But since like opposite poles attract each other, the Earth's north pole attracts the compass's south pole, which points north. I know it's a little confusing, but I promise it does make sense. So it points north. Just like we had electric field lines to help us understand the direction and size of an electric field, we also have these things called magnetic field lines. They're drawn to show the strength and direction of magnetic fields. Field lines close together, just like with electric fields, means that the magnetic field is strong. And I'm just going to show you what these fields look like. We're actually going to see for ourselves as a demonstration what the field lines look like for a bar magnet like this. We're going to do that in class. We're also going to see a demonstration where we're actually seeing how, we're not going to see the atoms align, but we're going to demonstrate how that happens and what the difference is. Okay, so let's see here. The magnetic field for a bar magnet, this is a bar magnet, this is a horseshoe magnet, looks kind of like this. You notice that the field lines start from the North Pole and point towards the South Pole. So that's an important fact to remember. They always start at the North Pole and point towards the South Pole. And you see that they kind of wrap around for a bar magnet. Lines go from north to south. If we were to put a compass here, remember the compass points towards, the part of the compass that points towards the North Pole, let's say it's this part, is actually the South Pole of the compass. The North Pole of the compass points towards the South Pole of the magnet. So if we put it here, the compass would be aligned like this. For a horseshoe magnet, we don't care about what happens outside the horseshoe. What you need to know is that the magnetic field lines point in this direction. So therefore, a compass would be aligned like this. Remember, the compass, the colored part of the compass points towards the North Pole, or for my compass, the arrow would point towards the North Pole. So therefore, that's the South Pole of the compass. Okay? Magnetic field lines are fairly straightforward to draw most of the time. You just need to remember the lines go from north to south, and also remember for a compass, the South Pole of the compass is what points towards the North Pole of Earth, or whatever magnet you've got it near. And again, we'll see what this actually looks like in class. We're going to spend a little bit of time talking about magnetic force. This is not something that you'll ever have to calculate yourself. What you will have to do, though, is understand how it works. An electric charge experiences a magnetic force if it moves perpendicular to a magnetic field, which is kind of weird. So imagine that you have a charge in an electric field. Here's my electric field. And let's say the charge is moving in this direction. Okay, there's the speed, there's the velocity vector for the charge. If it does this, if it goes along with the magnetic field, it experiences no magnetic force. It can still experience an electric force, an electrostatic force, but it experiences no magnetic force. On the other hand, if you have a charge and it moves like this, perpendicular to the magnetic field, it actually experiences a magnetic force. Now, why is that the case? It just is. That's just how it works. Okay? That's all you need to know. A charge that moves perpendicular to a magnetic field, that cuts across magnetic field lines like this, experiences a magnetic force. A charge that moves parallel to a magnetic field does not experience a magnetic force. So this leads to a really cool, interesting fact. If an electric charge moves perpendicularly through a magnetic field, it will actually start to move in circles that are perpendicular to the magnetic field. I'm going to draw this for you. We're going to draw a magnetic field. We're going to draw a magnetic field coming out of the page, okay, coming up like this. The way we're going to demonstrate this is, if I balance my pen kind of like this, okay, you can see the pen point and you know that it's coming out at you. Imagine that's how we're drawing these vectors. Imagine that these are arrows and you're just seeing the tips of each of the arrows pointing straight out of the page towards you. So we're going to draw a uniform electric field, same strength everywhere. And what happens if we take a charged particle and we shoot it into the field? Well, outside of the field, nothing's going to happen. But once it gets inside of the field, let's see, the particle is moving in this direction. The magnetic field is pointing up in this direction. The particle is actually going to move. This negative charge is going to start moving perpendicular to this, to the field. What that means is it's going to actually start moving like this. And if you let it go for long enough, you will actually see that it starts to make circles in your magnetic field. Again, why does this happen? Because the magnetic force is directed in, the magnetic force that gets put on this is directed in such a way that it causes it to move in circles. Why is it directed in that way? You don't need to know that. It's just because that's how it works. Okay? So the field out of the page means the electron starts moving in circles. Which is really weird, but that's what happens. Matter of fact, one of the best experiments that I ever did when I was in college involved charged particles, a beam of electrons moving through a gas, and a magnetic field was acting in that gas. There was a magnetic field set up, and the gas was in the magnetic field. And these charged particles, what would happen is they would smash into the gas. These electrons would smash into the gas. They would actually cause it to give off some light, and the light would actually show where the charged particles are. So you would actually get these beams, these circular beams of light in the gas, and that was actually showing you the track of the path of the electrons as they moved in a circular fashion through the gas. It was really, really cool. I'll find some pictures of it. The fact that this is what the magnetic force does is really important in, it has some really interesting applications. We're going to talk about electromagnetic induction now that's based on this idea of the magnetic force causes this kind of strange motion. Since electric fields and magnetic fields are very similar to one another, they have this interesting property. Changing the strength of one of the fields actually creates the other type of field. This is known as electromagnetic induction. Induction means you're inducing, you're creating something. What's being created is either an electric field or a magnetic field, depending on what you started with. So this means that whenever you have an electric charge or a magnet and it moves relative to something else, not only does it change its own field, it also induces another type of field. So think about it. If there's a magnet and it gets closer to you, that means that the magnetic field near you is getting stronger. Well, that's a changing strength of a magnetic field. That actually creates an electric field. And think about it. If you had no electric field to start off with, but now you have one, isn't the size of that electric field changing? So that changing induced electric field creates another magnetic field. And then that magnetic field is changing, so that creates another electric field. And the size, this doesn't like build up to forever. The sizes get weaker and weaker as you go, but you still get this pattern of creating and changing electric and magnetic fields. Okay? Basically, the long story short is that when moving charges create magnetic fields, moving charges will create magnetic fields around them, and if a magnet is moving relative to a conductor, like a piece of metal, that will actually create an electric field. And again, like we said, this is known as electromagnetic induction. And I know hearing about this without seeing the demonstrations is kind of like, well, okay, yeah, so what? I promise we will see these demonstrations in person, and you will see how this actually is applied. The other word you might, or phrase you might hear this called is Lenz's law. I'm going to give you examples, and we're going to show these examples in person in class. Maybe not these exact examples, but things based on them. A current carrying wire. Let's say we just have a long straight wire, like this. Current is flowing in this direction. Since charges are moving charges, they should create a magnetic field. And interestingly, the magnetic field that they create is not in the direction of current or against it, but actually perpendicular to it. You actually get these kind of like circular field lines that go out away from the wire. They create a magnetic field in the space around the wire that actually kind of wraps around the wire itself. It's a really neat thing. And the magnetic field actually gets it gets stronger as you get closer to the wire, as you might guess. So, current in a wire means charges are moving, which means a magnetic field is created. Okay? We're going to see a demonstration that proves that this happens. Let's do another example, or let's talk about another example, where you take a magnet and you drop it through a loop of wire. The picture I'm going to draw right here is actually an old-fashioned device for measuring current. Okay? You've got two little spots to stick wires in. You've got this little gauge here with a little needle, and the needle can move if it senses a current. Okay, so if there's a current, then the needle will move this way. If you hook up some wires to this, and you have a loop in one of those wires, and then you take a magnet and you drop it through the loop. If you take the magnet and do anything else to it, actually what happens is you don't really see anything. But if you take this magnet and you bring it through this loop of wire, you actually will cause, I mean, think about it, there is no, what's the word I'm looking for? There's no power source here. This is simply something to read the current. Okay? There's no power source. If you take a magnet and put it through this loop of wire, you will actually create a changing magnetic field in that wire. And what that will, changing magnetic field at this location, which creates an electric field. And that electric field will push the charges through this wire and cause a current. Because what's a current other than moving electric charges? If you have an electric field that's pushing the charges along, that's going to read a current. You don't need a power source in order to cause a current if you have a magnet and a loop of wire. So putting a magnet through the loop creates a changing magnetic field which causes an electric field which creates current. You have caused a circuit, a current to form without even a battery or any other power source other than a magnet and a loop of wire. That's really neat. We're going to see a variation of that in class. And then finally, probably my favorite demonstration, and the one that you'll get the most out of, is what happens if you put a magnet in a copper tube. Magnets do not stick to copper tubes. Okay, here's my copper tube. Copper is not magnetic, but it has this interesting property. It is a metal, so it does have free electrons. If you put a magnet inside a copper tube, it won't stick to it. But what it does is something very interesting. If you drop this magnet next to a copper tube, nothing happens. If you drop it next to anything else or through air, it falls at the normal rate you would expect, 9.81 meters per second squared. But if this magnet falls inside a copper tube, then what you might expect is at any location along the tube, you'll have a changing magnetic field because the magnet's either getting closer to that spot or farther away. As the magnet gets closer to, let's say, like right here, the magnetic field's going to increase. Since the magnetic field is changing, that creates a changing electric field. Okay, since you didn't have an electric field to begin with, and now you do, the electric field must be changing. And since you have a changing electric field, what that ends up doing is it creates a second changing magnetic field. But here's the thing. The second changing magnetic field, if this is the north pole of the magnet, this is the south, or vice versa, the created magnetic field is going to be opposite the original. It's opposed to the first field created by this. So think about what that means. If this is the north pole of the magnet, another magnetic field gets set up in the tube that has the north pole. So if this is north pole and this is south pole, at this location, as the magnet gets close to it, you set up a magnetic field that seems like the north pole of that magnetic field is up here and the south pole is down here. North and north repel each other. What ends up happening, and this is so cool to see, and I promise you'll get to see it in class, is that this second magnetic field that's opposed to the first actually repels the magnet a little bit. It still drops, but not nearly as fast. You can actually watch this magnet drop as if in slow motion. The magnet doesn't drop as quickly. And there's a million YouTube videos of this too, and they're really, really neat. Okay, so I know these notes were a bit weird. I'm kind of giving you a lot of information. What's important right now is that you have these facts written down pretty much as is. Because what we're going to do is we are going to take these notes and then we are going to do all of these demonstrations in class so you can actually see them and you can see how these things work. So it's really important that you have all these notes down because I'll be asking you questions from the notes, and then when we do the demonstration you'll say, oh, I see, this is how that works. Okay, so make sure that you have all this down, make sure you have all the questions answered. These are our last notes for electricity. I can't wait to demonstrate this stuff for you guys in class. It's really, really cool. Talk to you later.